Hello, my name is Sharmistha Bhadra, and I'm an assistant professor at McGill University in the Electrical and Computer Engineering department. So today I'm going to give a tutorial, it's a small tutorial on materials and technologies for printed and flexible IoT sensors. So too bad we have to do the tutorial in this way. Like I had a plan to do it in a more interactive way, but because of this COVID-19 situation, we have to do it in this way. But I'm pretty sure we're gonna see each other in some near future, and we'll be able to share our ideas and do tutorials in more interactive way. So let me start sharing my slide. So I guess you can see the slide now. So as you can see, so we're going to talk about materials and technologies for flexible and printed IoT sensor. So when we say Internet of Things or IoT, what do we really envision? So we envision that we have many sensors deployed in different application areas. So like let's say in home, in hospitals, in transportation system. So in home, let's say we have some wearables that is monitoring our health. There are some sensors that are monitoring the security of the home. Something is monitoring our power consumption or utilities that we are using. And the whole idea is, so there is all these sensors and they are monitoring different parameters, and then they are sending it to a central, like a central area through some gateway. So using the internet and using the gateway, it's sending all these things in a central database. And then people who need to use it, let's say doctors, they need to act on our health data, or even as a home user, we want to see how much utility we are using. So we can actually access those data. So our doctors can access those data from this network, and then they can give even feedback can be given through this network. So let's say if the doctors wants to, tell the patient, okay, you need to increase your dose of medication, they can just again send it over the internet to the patient at home. Similar thing we can assume in transportation industry, in different community level, or even national level for defense and infrastructure. So the whole idea is like we want to get all this information from around us, and then get it in a central place, and then people who need to act on those information or on those data access it, and then they look at it, and then they give what has to be done, and then they give a feedback um, to the people that were using those sensors. Or even sometimes you can think of like there are some actuators in different places, and the person that needs to look at the data look at it and then give their decision back to the actuator to work on a certain thing. So, this is probably the whole idea of Internet of Things. So we can vision that there has to be many sensors deployed in different scenarios. So now when we talk about Internet of Things, the main core is actually the sensor node. The sensor node has to be deployed in many locations. So when we talk about sensor node, this is actually the basic thing. And the sensor node basically consists of multiple sensors. And apart from sensors, there is also some other electronics part. For example, there is analog front end that reads all this data from multiple sensors. There has to be some sort of a microcontroller that reads the like that gets the data from the analog front end and does some processing on it. And then there is this wireless communication module that actually sends the data from the controller unit to the gateway. So if we think about it, there is the sensors, and then there is the other electronics part like analog front end and the wireless communication protocol, and also the microcontroller. So apart from the sensor, the other parts like the microcontroller, the analog front end, the wireless communication module, all these needs, because we need very fast processing now. So all of this module needs very fast transistors, and we need these transistors that are like really fast, and we also need to make like one of these, we need thousands of transistors. So thinking about if we need fast transistor, that means we need very small channel length in the transistor. So that's one requirement for this. Compared to these modules, like all these transistors with a small channel length, the sensors, they actually have a simpler structure. So they don't need a very small, most of the time, very small feature like a very fast transistor. So, so that's sort of like what we need in the IoT side. So what components we have and what we really, expect to have in them. On the other hand side, so let's look into the flexible and printed electronics. So printed so normally when we are using electronics these days, they are all made of they're made with conventional microfabrication technology. So there is all these standard CMOS processes or, standard silicon-based fabrication processes that we use to make them. Printed electronics is I wouldn't say it's a new area, but it is something that has been like printing electronics. The concept is there for a long time, but this is something people are exploring now in a different way because we have all these like fancy, all these very high tech printing technology available now. So which made us to explore printing electronics more than ever now. So printed electronics differ from conventional manufacturing technology, and it differs in two ways. So first of all, printed electronics is a additive fabrication process. So, and what that means is like when we are doing conventional microfabrication technology, you will see that to get a pattern, we do lithography. So it's a subtractive process. So we basically get rid of a lot of materials by doing etching. Whereas in printing, we just deposit the material where we want. So we don't really waste material by doing a etching process. So it's an additive fabrication process, which means it has less waste of material, and it also needs less energy consumption. Another important part is because conventional microfabrication technology, a lot of these processes are very high temperature processes, and we normally use silicon as a substrate. It's pretty standard. But in printed electronics, a lot of these processes are very low temperature process. So we really don't need to, we can basically use many types of cheap materials as a substrate, like paper, plastic type of substrate. So this allows basically, since we can use paper or plastic type of substrate, this means that we can actually make flexible devices out of printing technology. So if you can see, the benefit of flexible and printed electronics is basically it is cost effective. They require low energy consumption. They don't have much material waste, so the material waste is low. It's also a high throughput fabrication process. Like when we talk about printing, not in the lab, but in industry, we can assume that we are doing all this roll to roll processing like the way we print newspapers. So we can think that, okay, we can actually produce thousands of devices in a very short period of time. And finally, it also, we can think that, with flexible and printed electronics, we can get very lightweight, thin and flexible devices. So this is some example. This is a printed sensor that is basically works as an indicator, and you can basically put those printed sensor in a food package. It's a ripe sensor, so it basically indicates when the fruit is ripe. So it's a ripe indicator. And you can see this is another sensor that has been developed by a group at Stanford, and they're making a sweat sensor. So this sensor part is made of flexible sensor array, which is like some ion sensitive sensors, and the rest of the part they make it with conventional electronics part. So it's a basically combination of flexible and like conventional printed sensor and a uh, like a printed sensor and a conventional electronics part. So it's a mix of those two. So if we want to look at how actually how simple a printing process is compared to a conventional IC technology, you can see this is an example where we just wanted to see, okay, if we just need to print some like some interdigitated um, like metal conductor on a substrate. So this is basically a cross section of that. So where we have traces of metal on the substrate. And this is basically the cross section of the device that we want to make. So if you want to make it with a printing process, what we're going to do, we're going to take the substrate and we will deposit the metal ink wherever we need to deposit them. And then we do annealing or sintering of that to make the, to complete the process. So you can see there is only these two steps. Now, if we want to make the same thing with conventional IC technology, so again, we want to get this structure where which is same thing as we wanted to get with the printing process. So we have traces or interdigitated electrode made of metal on a substrate. So what do we need to do in a conventional IC technology? So we take the substrate, we sputter the material or the metal, and so it covers the whole area on the substrate. And then we deposit photoresist by spin coating. And then we bake the photoresist to make it hard. And then we do photolithography. So photolithography basically to pattern. So it's basically gonna, depending on what you use as a positive photoresist or negative photoresist, you're gonna get a, in the photoresist area, you're gonna get some change in the property. So in this case, the area that we blocked from the light, that area got chemically changed. So now, once we have the exposure, and then we bake the photoresist again. Then we will go for etching. And what the etching does is wherever it gone through the exposure, that area gets etched and the other area remains pretty intact. And then we get rid of this photoresist again, we strip them off, and then this is the final structure that we get. So you can see that to get the same structure, in printing process is only two step, whereas in a conventional microfabrication technique, we go through so many steps. So this can actually, even in a very simple case, it can give you an idea just to have these metal traces on a substrate, how many more steps that we needed to do with the conventional IC technology. So this is where printing process, you can see we don't have to waste materials that we got rid of, especially if we use noble material like gold, silver, titanium. This really matters, the cost. And also you can see the amount of energy consumption in all those processes were way more than the energy we consumed in this printing process. And finally, also you can see the like how rigorous this conventional IC technology process is. So now, and this is a question that I get pretty frequently. So you can see that, okay, it is very easy to do the printing process and it saves time, energy, material waste. So the big question is will flexible and printed electronics replace the conventional IC manufacturing process or conventional microfabrication technology? And in my opinion, I would say no. And I'll say the reason. I think they will be complementary, and we will use them in a way that, where printing process is more applicable, we'll use it there. And where the conventional microfabrication technology is needed, we will still use the conventional microfabrication technology there. So, and I mean, I see that the conventional microfabrication technology is still needed in many places because a printing process is simpler and it's also way faster manufacturing technique than silicon manufacturing. But the problem comes into when we are talking about the feature size. So with modern IC fabrication technology, we can have feature size as low as 20 nanometer. Now, printing, like all the printing processes we have, doesn't have that level of accuracy. So we cannot have a 20 nanometer feature with available printing processes now. Now, the problem, I mean, most of the printer can, even the very best one, can print feature of few micrometers. So you can think from a point of transistor that, something with a 20 nanometer channel length definitely will be way faster than something with a 20 micrometer channel length. So, and with all these, fast technique, fast computational requirement we have now, controlling microcontroller we want now, I think it's very difficult for, at least with the current technology available, it is very difficult to micro printing processes to compete with conventional IC manufacturing technique to make very, very high speed or very fast electronics. But we have to think about, like, not everything really need nanometer size feature. So let's say this is one example. So as we say, this is a sweat sensor. So there is these ion-based sensors that are flexible sensors, and the sensor part doesn't have nanometer feature. So this side still can be made with printing processes very easily because the feature size and everything is supported by printing process. Whereas the rest of the part, which has actually analog front end, controlling unit, and wireless communication unit, this part is difficult because we need high speed transistors and we still need to be compact. So this part, the rest of this electronics part is difficult to make with printed electronics. So this part we can still make with printed electronics, and the part that doesn't need nanometer feature, we can still make with printing processes, and then we can combine them. So that's why I say it's a complementary process because, as I said, it is you know, you can make different parts with different technology and combine them. And I feel personally that both of them will continue to improve and get help from each other. So, um, and this is what I think that hybrid way of making electronics is more efficient. So as I said, sensors are a pretty big part. I would think to make to use printed electronics technology. So if you see, if we make a chart, cost versus performance, so printed electronics will stay here. The cost is low, but the performance is not that great. You don't get that much good performance. Whereas silicon microelectronics, the cost might go up, but you also get high performance. So there are a lot of applications where you can still have performance in this range, and you can still lower the cost by using printed electronics. So this is a chart that is provided by ID Tech, and this is a forecast like how from 2011 to 2021, how printed electronics will flourish. And you can see over time that printed electronics is going to increase in market share, and a big part of that will be actually sensors. So by 2021, printed sensors will count for 2.1 billion market share. So that's pretty promising, and that actually also shows that sensors could be a very good application area for printed and flexible electronics. So, as I said, flexible and printed sensors are actually one of the prominent area of application for printed electronics technology. And the reason, as I said, the structures are more straightforward to fabricate them with printed electronics. Printed processes are normally pretty simple, and also the materials that are available for sensors are pretty there are a lot of materials that can be used for making sensors, and that could be also deposited using printing techniques. So these are the drive, basically people really looking into making sensors with printing and processes. So one of the thing is, printers, as you can see from the comparison of techniques, printed electronics is pretty, they are economically very attractive, but their of operational performance is not that great, like when you make the same thing with the IC silicon microfabrication technique. And the reason is because there are limitations in printing processes, the type of ink that we use, and also the substrate materials that we use. Another thing is, and I think this is a wrong thing to do, is the circuit topologies. So when we started making printed sensors, we still use the conventional circuit. So let's say we're making a SAW sensor or acoustic sensors, we still use the same design that we use in the conventional microfabrication technique. So, and I think I mean, that's not a right approach to do. So the motivation for this tutorial is to actually, or what we're gonna do in this tutorial is to gonna identify the root cause of some of the imperfection in printed, flexible printed sensors. And we're gonna mitigate some of this, or we'll show how to mitigate some of this imperfection. And so throughout the tutorial, we will cover a few things. So we'll cover conventional technologies and materials that are used for printed flexible sensors, and what is the limiting factors to use those conventional methods. And then we'll present some ideas like some emerging materials, some technologies, some other ideas, how how those could be used to overcome the limitation that is associated with currently available printed and flexible sensors. I'm going to also show, as I talked about the circuit topologies, like instead of using the conventional circuit topology, how can we go for new circuit topologies in printed sensor to improve their performance? And so throughout this talk, I'll also give examples of these things. Some of them might be from literature, but most of them will be something that I have done, my students have done in our lab. So let's first go into talk about materials. So when we talk about materials, so let's first talk about substrate, because substrate is something that's where basically holds the device. So the device is built on the substrate. So as you can see that in printed electronics, we are just not bound to use silicon as a substrate. We can use a lot of advanced materials for substrate. So the requirement that we need from substrate for printed electronics is we require flexibility in the substrate. We require excellent transparency and a special electrical characteristic in many cases. So let's say if we are doing a photovoltaic cell or a display, a lot of time we need transparent substrate. And let's say for other application, we might need other sort of properties. Sometimes we need some substrate to be piezoelectric. Sometimes we need them to be pyroelectric. So, we need different electrical characteristics from substrate sometimes. And then the thing we need from the substrate, we want the surface to be smooth. We want them to be thin and lightweight. We want them to be as much heat resistant as possible. And of course, we want them to be low cost, because the whole idea of using printed electronics is also lowering the cost. And finally, if we want to do roll-to-roll processing, and I think this is the final idea of doing printed electronics, is we want to print them like how we used to print newspaper in a roll-to-roll process. And for those sort of mass production, we definitely need the substrate to be flexible, because we need to roll them around a roller. So we definitely need them to be flexible. And also, these days for many applications, we are anyway looking for flexible substrate. Okay, so what are the options that we have for substrate? So one thing which is very trivial is glass substrate, and it is a very attractive transparent substrate. And glass substrate has been used quite a lot for displays, photovoltaic cell, lightings, and all this application. And the reason they were used for those optical purposes, because they have more than 90% transparency. And nowadays, you can get very advanced glass substrate, which are somewhere between 20 to 200 micrometer thick. The weakness, I would say, about the glass substrate, of course, is it's brittle. So you cannot really use it for it's brittle, so it's not that robust. They are way heavier than plastic substrate. And finally, the cost of the glass substrate is pretty high. So, to lower the cost and also to provide flexibility and robustness in printed electronics, people have been looking for more plastic and paper-based substrate. Excuse me. So when we talk about plastic or polymeric substrate, so there are a few that's actually pretty popular. So one is called PET. So it's very popular and it has been used in many printed sensor application if you see. And it has pretty good transparency. So the transparency is over 90% for them. So the benefit of having using PET is their low cost compared to many other polymeric substrate. However, they have few drawbacks, and the main drawback is the heat resistance. So we cannot really heat them up more than 130 degrees Celsius. And a lot of time, when we print materials on them, we need to bake them higher than 130 degrees Celsius to get good desired electrical properties in those printed materials. So, when we are using PET, we are very much limited by this 130-degree temperature limit, and that's pretty significant for many deposited materials. And then there is PEN and polyimide. So both of them have better heat resistance than PET, but polyimide, which we call normally Kapton, that has the highest heat resistance. You can even heat them up to 400 degrees Celsius, so which is very good. But of course, polyimide, it is way higher cost than PET. And also the transparency of polyimide is lower than PET. And then there is another, so depending on what you really need, like if you can still lower, like you can bake your things at lower temperature, you can go with PET. And if you really need to go more than 130 degrees Celsius and you still need to have flexibility, the better option is to go with Kapton or this polyimide substrate. And then there is this special polymer substrate, which is called PVDF. So polyimide is has a piezoelectric property. So, it has a piezoelectric charge coefficient of around 15 to 30 picocoulomb per Newton. They're flexible, and you will see that for a lot of flexible acoustic sensor, they are widely used. The drawback is again the poor heat resistance. So we cannot really heat them up more than 160 degrees Celsius. So we are limited by this temperature range. And another thing is also the lower charge, piezoelectric charge constant compared to the rigid piezoelectric substrate. So conventionally, what we use for piezoelectric substrate is quartz or PZT, and those has piezoelectric charge coefficient, which are more than like 200 picocoulomb per Newton. So definitely when you make acoustic sensors out of those PZT or quartz, definitely the sensitivity you get out of them are way higher than what you make with PVDF. So, so the sensors, of course, have lower sensitivity, so they are lower performance than the one that you make with rigid substrate using conventional microfabrication technology. So what I'm going to talk about next is we were trying to make some acoustic sensor, and we were thinking of making flexible piezoelectric substrate with that has high piezoelectric charge constant. So to make that, yeah. So yeah, so the whole idea was we wanted to go for a flexible piezoelectric substrate, which had higher piezoelectric charge coefficient, so we can make sensors with the flexible substrate, acoustic sensor with the flexible substrate, but that has higher sensitivity. So in order to do that, we basically went to make piezoelectric composite as our choice for piezoelectric substrate. So what composite does, it basically combines the high piezoelectric charge coefficient and the dielectric constant of piezoceramics like PZT with our barium titanium oxide with the flexibility and the low density of polymer. So the composite can have tunable piezoelectric or electric or mechanical properties. They can be made biocompatible by choosing the right like piezoelectric ceramics. And then we can make them with very simple processes. So they are pretty good for mass production. And then this composite, they're very flexible, so they can be used for roll-to-roll printing processes. So composite, how you mix or how you embed the ceramic, piezo ceramic in the polymer matrix. You can embed it in different configuration, and how you do it depending on that you have different configuration like 0 1 0 0 1 2. So these are all different configuration that you can have. The simplest one is the 0 3 configuration. So in 0 3 the particles, the piezoceramic particles are randomly dispersed in a polymer matrix. And it is out of all these configuration, 03 is the one that can be made very easily. So as you can see, we basically made a piezo composite out of piezoceramic, which is PZT, and the polymer matrix was made from PDMS. So you can see the way we made it is we had a PZT nanoparticle, and we had PDMS based polymer, and we have curing agent. So first we mix the PDMS based polymer with the curing agent into a 10:1 ratio, and then we disperse the PZT nanoparticle in the polymer matrix. And then we basically did stirring, pretty rigorous stirring for 30 minutes. And then after the rigorous stirring, we basically deposited the solution on a FR4 board, and we did spin coating. And after that, we did curing. And after curing, the PZT PDMS film very nicely peels off from the FR4 board. So you can see that these are basically the film that after we peeled off, and you can see how flexible they are. You can even wrap it around a pen. So, this composite, after you make it this way, they don't show very high I mean, they show sort of, decent piezoelectric charge coefficient, but we can improve the piezoelectric charge coefficient further by doing corona polling. So, in corona polling, we basically put the film under a very high electric field, and that basically aligns the dipoles of the ceramics in the film. So we did the corona polling, and this is basically an SEM image of the film. And you can see it's just to show that these PZ, because the particle has to be, the nanoparticle has to be dispersed in the pieces in the polymer matrix very well to behave like a good piezo composite. So we took the SEM image, and you can see that the particles were pretty nicely dispersed. So we made the film, and this is basically showing a 28 volume percentage PZT film. And as I said, we choose the 03 composite because it is easy, like we can just manufacture it by simple manufacturing process like steering and spin coating. Okay, so then after we made the film, we basically packaged them with 2 flexible electrodes. So the electrodes were made by printing silver layer on a Kapton film, and then we basically sandwich the film across those flexible between those flexible electrode. And so this is how the packing looked like. And we basically did that and we measured the we can measure the voltage generated across those flexible electrode. So once we pack them, you can see that we can basically bend them very easily. So what we did is we wanted to see if it actually shows piezoelectric response. So we take this packing, and then we basically bend them. You can see the direction, we bend them, and we measure the voltage across the electrode. So you can see so these are basically 5 different volume percentages of composite film. So one is for 3.5 volume percentage PJT. The green one is for 8.2 volume percentage PJT. The green one is for 11.3. The magenta one is for 13.3, and the cyan one is for 28 volume percentage PZT. So we basically did those bending tests for poled and unpoled film, and you can see that we do generate open circuit voltage, which follows this equation. And you can see that this G15 basically depends on the piezoelectric charge coefficient D15. So you can see that compared to the unpoled films, the poled films basically generate 4 times higher voltage. So that means by polling process, we do increase the piezoelectric charge coefficient quite a bit. So that shows the effectiveness of the polling, and this results also shows that the films really act like a piezoelectric material. So then we also wanted to see how flexible they are. So we did a tensile test. So you can see that as we increase the volume percentage of PZT in the composite, the Young's modulus starts going up. So basically, as we increase the PZT percentage, of course, our volume percentage PZT in the composite, our piezoelectric charge constant increases, but at the same time, our material starts losing flexibility. But just looking at this Young's modulus number, you can actually see that even with 28 volume percentage PZT, the sensor, the material is still very, very flexible. And we also measured the dielectric constant of those films. So you can see that as we increase the volume percentage of the PZT in the composite, we do increase the relative permittivity, and also we sort of um, showed if it follows the model. So you can see the, we basically put the Yamada model and the Lichtenstein model for composite, and you can see that it, like at lower concentration, it does follow the model pretty closely, and at higher concentration, it starts deviating from the model. And then finally, we wanted to measure the D33 piezoelectric charge coefficient. So we took the films of different volume percentages, and we applied 0.5, 1, and 1.5 Newton step force in all of those fold films. And from those, and this is the response for charge that we generate. So these blue ones are the force that we apply. So you can see that for each field, we do 0.5, 1 Newton, and 1.5 Newton force. And then we measure how much charge is generated. So, and from those we can calculate the piezoelectric charge coefficient, and you can see that with how with increase of volume percentage, how the piezoelectric charge coefficient D33 starts increasing. So, with 28 volume percentage, we have a pretty good piezoelectric charge coefficient, almost around 78 picocoulomb per Newton. And also, as I said, just looking at the number for the Young's modulus, this 28 volume percentage film is very flexible. So it is a very, it is a film that we can actually use to make sensors. So also, apart from using this as a later on for acoustic sensors, we also wanted to see, because this is a very nice flexible film, we can actually even use it as a tactile sensor. So we took the film, we printed electrode. So basically, it's the same way that we did the sandwiching between two printed electrode. And then we basically touched that film with finger. So basically, we basically applied different forces by finger, and you can see that for different forces applied by the finger, how the charge response changes. So you can easily see that we can actually sense very small force. So we can even distinguish between very small force differences with this film. So this has a pretty good potential to be used as a tactile sensor. So we can use it in robotic skin, or we can even use this in other flexible tactile sensing application. So all this results on this composite, along with some more experiments and other results. That paper actually was published in IEEE Sensors last year, IEEE Sensors Journal actually. Okay, so we talked quite a bit about substrate. The next thing I wanted to talk about is conductor. Actually, mostly printable materials, and first we're going to look at conductor. So we know that conductor is a very big part of any electronic devices. And if we look at conventional, electronic devices, we'll see that more, metals are the one that has been widely used as conductor. So now the difficulty of using metal directly for printed electronics is because for printed electronics to deposit material, we need to make ink out of them. And metals, so we need basically some solution. And metals cannot be directly dissolved. If I bring a piece of silver, I cannot directly dissolve it in some aqueous or organic solvent. So what really enables to use metal in printed electronics is called nanoparticles. So we basically, instead of dissolving a metal, we make nanoparticles out of this metal, and we also add some surfactant on them. And these nanoparticles, with those surfactant on them, can be very well dispersed in many organic solvent or water. So, and when we make like a solution out of them with surfactant, we actually call them inks. So one of the thing about these nanoparticle based ink is they mostly have low viscosity. So, and we know that for high resolution printing, we need to have low viscosity ink. And that is mostly done with inkjet printers. So, nanoparticle based ink really supports that. And so another thing is, after we print them, these ink, so and we need to dry, because these solvents are sort of a coating, also the water. So we need to get rid of these solvent and water. And then we want the metal nanoparticles to be like really in close contact with each other. So many times, and also you'll see later, many times we need these nanoparticles also to melt and form neck with each other, and finally form a pretty uniform film. So all these require pretty high temperature processing after we deposit the ink. And as we know, many flexible substrates, they cannot really withstand high temperature. So as I said, they are not, sometimes some of these inks are not suitable for many flexible substrates, something like PET. The benefit of using metallic films are they provide high conductivity, but you'll see later they have poor mechanical properties. So when we use them on flexible substrate, and if we bend them, they tend to get cracked, and it also have adhesion issue with plastic substrate. So there is also reliability issue. So we're going to talk about those, and we're going to see how can we get rid of those problems. So as I said, we can make ink out of nanoparticles very easily. And as I said, there will be in the ink, there is a surfactant that is around those nanoparticles, and there is also the solvent that you disperse the nanoparticle in. So once we deposit the ink, as I said, we need to bake them. So first of all, at some high temperature, all those all the solvent, all the surfactant, they starts burning off, and they starts going off from the deposited ink. So that's the first thing we want. And then after that, we have these nanoparticles that are sitting side by side. And what we want is to have a good uniform film, just not nanoparticles sitting side by side. We want a uniform film. So this nanoparticle needs to form a neck. They needs to melt into each other, and needs to form a basically uniform film. And for that, we need further increase in temperature. So with that further increase in temperature, this nanoparticle melts, and they starts forming a very nice uniform film. So that melting temperature, if we want to use flexible substrate, that melting temperature has to be as low as possible. So that's why also this melting temperature of the nanoparticle, they go down as the particle size go down. So if the particle size diameter is below 20 nanometer, the melting temperature decreases rapidly. So we want to use as low temperature, as small particle as possible to make the ink. So So basically the temperature issue can be solved if we make, the ink with, nanoparticle that are smaller than 20 nanometers. So the temperature issue of baking the ink or sintering the ink can be solved by using um, lower size nanoparticle. So other than the high temperature sintering issue, there is another issue which is called the adhesion issue. So when we print the metallic ink directly, um, let's say when we are directly printing metallic ink on the PDMS um, surface, that the composite that we built, we could see that it has very bad mechanical stability. So if we bend the substrate, it starts getting cracked, and also it easily pans off. So there is not good adhesion between the ink and the substrate underneath. And it's true for any polymeric, like plastic type substrate. So it's just not for our substrate. If you use any polymeric substrate, you're gonna come up with this issue. So and also when we're doing elongation, the metallic silver inks were coming off. So and the way to improve it is basically we need to improve the adhesion between the metal layer and the polymeric substrate, which is in our case was the PDMS surface. So there are surface modification technique that has been used to improve um, the adhesion between the metal ink and the um, polymeric substrate. So there is something called plasma treatment, there is primer and binder application process, there is corona discharge treatment. So people have employed different things. Uh, so we wanted to see which one works for us. So the reason we didn't want to go for primer and binder technique is because it needs extensive study and preparation for the synthesis of the primer and binder chemicals, and because you need to like play around with those primer and to get basically the best adhesion property, and it needs a lot of synthesis of matter chemicals. UV or ozone or corona discharge techniques are easy and compact, but there is not too many parameters that you can play around with to optimize the process and get the best adhesion property. On the other hand, plasma treatments are not that complicated, but it also showed pretty good capability and effectiveness to prepare the surfaces for adhesion. So we used plasma treatment. So as I said, in our case, the PDMS and the metallic printed ink doesn't adhere very well. And as I said, the reason also because the PDMS surface is hydrophobic, and there is also a very big stiffness mismatch between the polymer composite and the metal. So of course, that's why they don't adhere very well and we get cracked. So we did surface plasma treatment. We basically use two types of we did variation in the treatment, and you can so this is basically a film that basically a metal layer that we printed on our film, and we didn't do any surface modification technique. And then after printing it, we did some tests. We put it in the ultrasonic bath, and before and after, you can see that part of it is washed away. We did tape tests, so we basically put a tape on this metal layer, and then we took the tape off, and you can see that it totally comes off when we peel it off. And then we also did a soak test, and in soak test you can see that before and after there is not much difference, but of course the untreated film cannot keep the metal layer with ultrasonic test and the tape test. So we did change a few parameters, and while we did the plasma treatment. So we changed the type of gas, the type of pressure, the treatment time to get optimized results. And we to test things how well this is working, we basically did some measurement with contact angle. Yeah. So as we said, yeah. So as we said, the solution is like we did plasma treatment and we also analyzed it using different parameters. So we basically used two types of plasma treatment. One is low pressure plasma treatment and the other one is atmospheric pressure plasma treatment. So for low pressure, we used two conditions, one with plasma polymerization and the other type of treatment is surface etching. So for the plasma polymerization, we used this combination of these two gases. And for surface etching, we used argon. So here you can see the parameters that we used. And for atmospheric pressure plasma treatment, we used nitrogen gas, and you can see the parameters that we used. So after we did the plasma treatment of the film, we did measure the surface atomic composition. So you can see this is just regular pristine PDMS. And then we did with low pressure argon treatment, this is the composition. And then this is with low pressure have the plasma polymerization treatment, and then this is the atmospheric nitrogen treatment. So you can see for both cases, for argon and nitrogen plasma treatment, the amount of oxygen functionalities on the surface got increased. So you can see the oxygen got increased, which is the green bar here. And and the reason it happens is because this both cases it's an etching action. So the plasma removes away the top surface and it basically exposes the deeper functional group. And then the etching action also leads to presence of certain reactive group on the surface, which tends to bond with atmospheric oxygen, and that's why the oxygen increases. And it also so you get surface on the surface functional group of oxygen and nitrogen. So the increase, so in both of these cases, the oxygen to carbon ratio increases, and it basically indicates that the oxygen containing groups are formed on the surface, and this basically this oxygen functional group forms like a silica-like layer, and it forms a hydrophilic surface. On the other hand, when we did the polymerization process, so we did with a combination of the carbon dioxide and this gas, and you can see that in this case, of course, the amount of carbon increased. And as I said, it's the plasma polymerization process. So in this study, the ethylene, as we said, we used ethylene and carbon dioxide. So ethylene is an organic gas, and it basically, when we do a plasma polymerization process, we create a polymerized layer of ethylene on the top of PZT PDMS surface. And then after we add the carbon dioxide, it is basically works as a heterodome source, and it creates oxygen-rich functional group, which are like COOH and CHO. And it's basically these functional groups are formed on the layer of polymerized film. So this COH and CHO, oxygen-rich functional group, this basically makes the surface hydrophilic. And then we also looked at the contact angle. So it's basically the idea is as the contact angle goes lower, the surface becomes more and more hydrophilic. So here are the contact angle measurement. This one is basically A is just a regular surface, and PZT-PDMS surface is an untreated one, and you can see that initially we have a contact angle around 110 degree, and then for treated ones, so we have B is basically the one done with plasma polymerization process, and you can see we lower the contact angle to about 35 degree, and then the C is the contact angle for the argon plasma process, and you can see the contact angle also gets lower. The average is around 20 degree, and for the D is the nitrogen one, and you get an average of around 18 degree. So this is sort of average, sorry. The argon was around 35 degree. And so C is actually the, so the C is actually the plasma polymerization with ethylene and carbon dioxide. So you can see that by the plasma treatment, we do lower the contact angle immediately after the treatment. But as we leave the surface open, over time the hydrophilic property starts decreasing, so it gets washed away, and the contact angle starts increasing. So you can see that after 48 hours, this is what we measured as contact angle. So definitely we can see that the nitrogen one actually gives us a lower contact angle right after the treatment, so it's pretty effective. But we can also come to the conclusion that once we do the treatment of the film, we need to print the metal layers or the printed layer as fast as possible, so that it doesn't or the surface doesn't become hydrophobic over time. So that's very important part, that we need to do the treatment as fast as, like the printing as fast as possible. So then we did some adhesion tests. So we printed a pattern on the different films with treated with like untreated and treated with different, as we mentioned, with different processes. And then we did ultrasonic tape test and soak test. And you can see that, and these things were printed right after treating the surface. And you can see that the nitrogen one, basically the pattern survived all of those tests compared to, that gives the best results. So then we proceeded with the nitrogen treated film to see how electrically and mechanically they're stable. So we had, we pasted the film on a Kapton film, and then we printed a silver layer, and then we basically did bending and releasing of the film with the metal layer, and we measured the resistance of this printed layer by applying a voltage and measuring the current. So you can see that how the resistance, normalized resistance, changed for different bending cycle and releasing. So you can see that the normalized resistance or the electrical property didn't really change much. Actually, didn't even change significantly for bending and releasing. So that means that if we treat and also the film was mechanically very stable, so which we can also see in this test. So we can say that these films where if we treat the film or the substrate with the surface modification technique, and we can print the layer, they can be really good for flexible application in terms of durability or the adhesion issue. And other than the metallic inks, there are other options for the conductor. A very emerging option is composite conductive polymer. So it basically incorporates a large amount of conductive material, and we disperse it in a matrix of polymer. It's basically the composite. And so as I said, polymer is not itself conductive, but it acts like an adhesive. And conductivity is basically realized by blending or dispersing conductive nanoparticles or powder in it. It's very simple and low cost to prepare this composite, and they can be very flexible, and they need low temperature processing. One of the important thing though is to know how much we need to add. So this is which is called the percolation point. So we basically need to. So let's say here is an example where some conductive particles are dispersed in a polymer matrix or insulative matrix. But you can see that there are few and they're not connected to each other, so they don't make a conductive path. So as you increase the conductive filler, eventually they form path conductive. They fulfill the path in the matrix, and you get conductivity in it. So if you measure the conductivity versus the filler concentration, this type of curve is something that you want. So you always want to get something that is want to mix something that is after the percolative zone. But after the percolative zone, so let's say you add this much of amount, it doesn't matter how you increase much more after that, you're gonna get pretty much the same conductivity level. So when we make this kind of ink, the idea is we mix actually basically we choose this amount, because if we increase if we choose something here for the filler percentage, we're still going to get good conductivity, but the more filler we add, it's going to lose the flexibility. Another very good option is also P-dot PSS. So it's basically a mix of two ionomer. One is P-dot and another is PSS. And the good, very nice properties about P-dot PSS is they're transparent, so they can be used for many optical devices. They have high ductility, so they can be used for flexible application. We can actually add some other stuff like sorbitol and surfactant in this P-dot PSS ink, and we can increase the conductivity. Also, there are ways to increase the conductivity in a post-treatment process. And the good thing about it is they need low temperature processing. So so we looked into conductors. The next important material that we're going to look into is semiconductor. So semiconductor for printed electronics can be actually divided into two categories first. First is the organic semiconductor, and then is the inorganic semiconductor. So for organic semiconductor, we have small molecule semiconductor and then polymeric semiconductor. So small molecule semiconductor, the great benefit of them is they can be purified very easily. They can make a very nice polycrystalline or single crystalline film, and that's what we want in semiconductor layer. We don't really want amorphous crystal. We want polycrystalline or single crystal. Also, we can make very low viscosity ink from them, so which helps with high resolution printing. Um, um, so one of the problem is like the inks that we make out of them cannot be easily processed into high quality film. They have very low mobility, and also they are very sensitive to environment. Whereas for polymeric semiconductor, they have good flexibility. They are suitable for low temperature processing. We can have we can make the polymeric semiconductor. We can design them so we have a lot of wide varieties. But it has low mobility, and the on-off ratio is low. Now, for the inorganic semiconductor, they have higher mobility and on-off ratio than organic semiconductor. They make normally polycrystalline film, and they are environmentally stable. But the problem with them is they need high temperature processing. So for organic semiconductor, the more, I'm going to give an example which is very commonly, can be commonly used to make our devices. We'll call pentasyn. So you can see there basically have, it's a compound. It has consist of benzene, fused benzene rings. It is probably the most studied small molecule semiconductor. People have shown that, if you can do the right processing, you can actually make single crystal out of them. Um, and then, one group, they have showed that they can achieve a mobility of around 35 centimeters square per volt per second with pentasyn. One of the main problem with pentasyn to use in the printed electronics is they don't like to dissolve in common solvents, so it's difficult to make ink with them. And they also have poor environmental stability. So as soon as we make a transistor out of them and we measure things in vacuum, it seems fine. And as soon as we bring them out in the environment and measure things, they can act totally different. So the solution, the problem to make a solution out of them can be solved. That can be solved by substituting an acid compound. So mostly you can add a silicon alkaline group at the C6 and C13 position of pentasyn. So adding that really helps with mobility. It increases the mobility. At the same time, it increases the solubility. So I would suggest, like, if you really want to use pentasyn, not to just go for regular pentasyn ink, to go for TIPS pentasyn, because that's going to give you better performance in the printing process. So pentasyn is a p-type material. And unfortunately, it is a very, we don't have really available n-type small molecule material that are environmentally stable and at the same time have high mobility. There are few n-type small molecule material, but the mobility is really, really low, and environmentally they are really unstable. Then for the polymeric semiconductor, the most common type that we can buy as an ink is P380. So it's a p-type material, and depending on the structure, we can have, basically it has an alkyl group, and where the alkyl group is situated, we can get 3 different configuration for P380, tail-tail, head-head, and head-tail. So among these 3 structures, I would suggest to use the head-tail one because it has a well-ordered morphology, and so it gives a better mobility and has a pretty good on-off ratio. And again, like a small molecule material, the polymeric semiconductor also has the same problem, where there is not a very good n-type polymeric semiconductor that is environmentally stable and at the same time has high mobility. So how can we also, there are ways that we can increase the P380. more performance. So one is actually because these are polymers, so we can go for longer chain. And if we can increase the average molecular weight of P380, we can increase the mobility. And then we have all these alkyl chains, so we have to choose a structure because polymers can be made in the lab. So if the alkyl chain is too long, it's basically we get low mobility. At the same time, if it is too short, then we get low solubility and film forming ability. So, it's very important to choose a right size for the alkyl chain so that we have decent mobility, solubility, and film forming ability. Also, the side chain that it has, if it is too bulky, it can actually lead to poor molecular ordering and low crystallinity. And the distance between the so low crystallinity. And the reason is because if we have a bulky side chain, basically the distance between the PT backbones increases here, which actually results in lower mobility. And the fourth thing to look at is the solvent that we use. If let's say this is an example, if someone uses chloroform as a solvent, they get a mobility of around 0.1. If someone uses THF as a solvent, they get a solvent around mobility around 6 times 10 to the power minus 4. So you can see that it does really matter what you use as a solvent. And then we can look into some inorganic semiconductor. So among different inorganic semiconductor, the single wall carbon nanotube is the most attractive one. So so we can use individual single wall carbon nanotube as a semiconductor material in a transistor channel, or we can use film. So the problem to use individual or aligned array of single wall carbon nanotube is they're too complicated to do in a large scale. So they're not very suitable for a large area fabrication. So what people mostly go for is random network of single wall carbon nanotube because it's easier to form them and you don't have to manipulate individual carbon nanotube. So the major challenge to use semiconductor type of single wall carbon nanotube is when we produce single wall carbon nanotube, they are not pure. So you have a mix of semiconductor and metal one. And even if you have, so it's very important to do a sorting to basically make the semiconductor one as pure as possible. Because even if we have a few metallic carbon nanotube in the mix, it's gonna cause a very low on-off ratio in the transistor, and even we can lose totally the pinch of point. So most of the single wall carbon nanotube, they are p-type in nature. Many have approach that there are many approach to basically switch the single wall carbon nanotube from p-type to n-type. So there is chemical doping, there is ion implantation method. So the good thing about them is single wall carbon nanotube has very good mobility. So you can get something even up to 30 centimeters square per volume second, and you can get an on-off ratio between 10 to the power 4 to 10 to the power 7. So single wall carbon nanotube is a very good material, and you can make printed inks with them. So it's a very good material to use in a printed transistor. And other than the single wall carbon nanotube, another inorganic semiconductor we can use is like the metal oxide semiconductor. And the most popular one is indium gallium zinc oxide. So they give pretty good mobility, they give flexibility, they are environmentally stable, they can be also optically transparent. people can achieve mobility of more than 10 centimeters square per volt second, and you can even get an on-off ratio of 10 to the power 7. Um, the only problem of using this inorganic metal oxide semiconductor is um, they need once I mean with the once we make solution and we deposit them, we need to like anneal them at high temperature. The higher temperature you will anneal them, the better mobility you get. But that sort of makes them not compatible with polymeric substrate. So that's one problem they have. Another thing is indium, as they say that is indium gallium zinc oxide has indium, and indium is a rare earth element. So people have switched from indium gallium zinc oxide to zinc tin oxide, so ZTO or this type of material, but all of these actually require high temperature annealing. So that's the one problem with metal oxide semiconductor. And finally, we're going to look at also some of the dielectric material, because dielectric material is very important to make capacitor and the insulating layers. So to be honest, there is a lack of printable dielectric material. So you'll see that dielectric materials are like rarely printed. They're mostly like, even if you make solution out of them, you just deposit them, techniques like spin coating and something like that. So one thing is a dielectric layer. We want them to be thick so that we don't have leakage current. But at the same time, if we want a large capacitance and that's what we want in printed dielectric layer, we need it to be thin. So for leakage current, we want it to be thick, but for higher capacitance, we want it to be thin. So how do we get around with it? The way to get around with it is making it thick, but at the same time having a high dielectric constant in the dielectric material, so that even with a thick um, layer, we can still have a high capacitance. So there are different solution processable dielectric materials, polymer-based, inorganic, oxide-based, ion gel-based, solid-state electrode-based. Ion gel and solid-state electrolytes have pretty high dielectric constant, but they also have high conductivity at high frequency, which can limit the switching speed of transistor. People have used zirconium oxide, which is solution processable, but they also have high permittivity, but it also has high frequency stability. But the problem is it gets pinholes and cracks that can eventually lead to short circuit of the devices. Um, there are polymer-based dielectric materials, but they have low permittivity, but you can print them. So there is one of a very great thing to do is to use dielectric composite. So you basically mix nanoparticles of high dielectric nanomaterials with a polymer, and you make a composite. So they normally have high dielectric constant. You can print them easily, and they also have high frequency stability. So this equation basically defines what will be the final dielectric constant of the composite material, so you can mix things in proper proportion. So even just looking at the equation, you can see that the dielectric constant generally increases as you increase the loading of the nanoparticle, but also the leakage current increases with the increase of the nanoparticle loading. So you have to be careful when you make this type of composite for dielectric, that what will be the best optimized volume percentage that you mix with the polymer. So next we're going to talk a little bit about the printing processes. So as we know, there are a lot of printing processes available for electronics fabrication, like inkjet printing, aerosol printing, screen printing, all this, etc. So how do we choose a right printing process? So, there are a few things that we look at when we choose a printing process. So if we already have an ink, we look at what is the viscosity of the ink. If these are low viscosity inks, then we have to go with processes or printing process that supports low viscosity. Um, if it's high, then we go with something like screen printing. There is another thing that also we need to look at is how the ink is compatible with printing components. So depending on what printing process used, like some have doctor blades, some have inkjet inks. So how compatible the ink is with all these components. The third thing we really need to look at is what is the resolution and accuracy that we need and what the printer can really support. The fourth thing we need to really look at is the uniformity. So because some devices might need 1 micron uniformity all across the substrate. So some might need few centimeter, can tolerate few centimeter, and so what our device can tolerate and need based on, and what our printer can offer, based on that we need to choose the right printing process. Also, other things to look at is also the throughput and cost, because many times we want to fabricate things that are, um, you know, um, that are lower in, cost, and we also want to get things done very faster. So, depending on what printing process we use, things can take different timelines to print devices. We also want to see which one can adopt roll-to-roll processing, because it can increase the fast print. It's basically uh, fast or speed of making device at a reasonable cost. We also need to look at what is our substrate, because not every printing process can support every substrate. So substrate plays a role to decide on our printing process. Um, as I said, we also need to look at how can we do the wetting control and how the interface, how can we form interfaces. So all these different things that we have in a printing process that we, and I mean, when we choose a particular printing process, we need to look at like things from different angles. And these are some of the things that you can bear in your mind, that when you choose a printing process, what to look for. So printing processes can be normally divided into two categories. One is without template and one is with template. So without template one, something like inkjet printing. And these are very good for lab purposes, because where we are trying with different design, different things to finally come up with a final design. And you can see that without template, processes are pretty good for lab fabrication. Whereas in the industry, when you have a final design, you can go with something that with template and the fast process like gravure printing or something like that. So different printing methods actually requires different viscosity ink. So low viscosity inks are really sought in a process like inkjet printing and gravure printing, whereas the high viscosity inks are required in a printing process like screen printing. So low viscosity inks can make form smaller features, but the problem, one thing we have in low viscosity ink, something called coffee ring effect. So when we deposit a high viscosity ink, like here, we wanted to get this rectangular feature. Because it's high viscosity, it doesn't flow much and it forms a nice pattern. Whereas for low viscosity inks, once you deposit, because it has low viscosity, it tries to flow outwards, and it sort of forms a coffee ring like that. This is basically the cross section. And this coffee ring effect can be very, very detrimental for devices. This is an unwanted effect. You don't want it. So this is something not really desirable. So what you at least want is semicircular arc, something like that. This is very difficult to get with low viscosity process, but this is something what you want. And in order to get that, you have to basically do some surface treatment of your substrate before you deposit the ink. So I just wanted to give an example where a choice for printing went wrong. That was, we wanted to make a microstrip line coupled to some open loop resonator. So we designed this. So we had a substrate, and for the substrate we did some simulation, like calculation, and we found that we need a gap of 0.05 millimeter between the resonator and the microstrip line. So this is the S. So so to go for this a small feature, like the available printer we had, only the aerosol jet printer could print get a gap something like that. So we did use the aerosol jet printer, but when we made the resonator and measured it, so the blue line is the measurement, you can see that our quality factor went down, whereas in the simulation, we have very nice quality factor. And the reason is because the simulation was optimized and it was done for a 50 micron thick pattern. But when we did the pattern with aerosol printing, the patterns were 5 micrometer thick. And as we lowered the thickness, it basically increased the loss and it lowered the Q. So what was the solution in this case? So of course we didn't think about it before. And you can see that we ended up with a wrong printing technique and get a lower sensitivity or lower Q in the resonator. So what was the solution to basically for this problem? So one thing is we can print multiple layers by aerosol printing, but that's also not a good option because as we do more and more layer, we're gonna get more and more spreading around in the gap area, which might eventually short the resonator and microstrip line. So the best solution is to actually choose a printing technique that could support a 50 micrometer gap and at the same time 50 micrometer material thickness. So you can see that how important it is to choose a right printing process. And so once we choose the right printing process for us, we have to do some processing, which we call pre-printing process. So, and it really matters because if we don't do the pattern design properly, we cannot get a final nice printing pattern. So the pattern that so we can do a lot of this modification in the pattern design stage. So the pattern used for inkjet or gravure or screen printing are basically, these are composed of, so any pattern is composed of matrix or dots. So in inkjet printing, we need to determine what should be this dot spacing. If the dot spacing is too large, then we will get individual drops of ink, but they won't be connected. And if the dot spacing is too small, then we will overlap the dots, and which will cause a bulging of printed line, which will reduce the uniformity and reduce the device performance. So the dot spacing we have to choose depending on the ink movement and the droplet value. So this is very important. Same thing with again, for gravure printing, the gravure has cells like patterned on the blade, and we need to decide on the cell size and the width properly so that we get a nice pattern. So it's important to actually choose this thing in the pattern design. Same thing for the screen printing. We need to choose the right mesh size and fabric diameter so that, and it should go according to the ink property and interaction between the ink, the screen, and the substrate. So pattern design is very important. How we choose the dot spacing, how we choose the gravure blade, how we choose the screen. And then also another thing is the surface modification technique. I'm not going to go too details into it, as I already talked about the surface modification technique in the metal conductor part. Like we saw that many times the ink doesn't adhere properly and we need to do some treatment of the surface to get better adhesion and durability of the printed layer. Um, Also for paper-based substrate or textile, because these are pretty rough surfaces, so it is difficult to print directly electronic component on them. So we normally want to smooth the surface before the printing by some coating. And the last thing in the printing process is important is the sintering, because we know as we deposit ink, we already talked about it. They have surfactant, organic materials, solvent in around them. So we need to get rid of them, and then we need to even increase the temperature to get a neck formation between nanoparticle to get ink. Nice conductive pattern or other kind of pattern. Sintering is very important process. It is important to improve the electrical property, especially for particle-based ink. Um, so normally we do sintering on hot plate and or in oven, which is the best way. It takes long, but it is actually ideal process. But it does hit the whole device, and many times you don't want that. So let's say if you want to save some area from heating, what is not normally used is a focused light beam heating type of technique, which just selectively heats up some area. And also people have used microwave heating, which is also pretty fast heating process, and it is also pretty uniform. So the last thing I'm going to talk about in the tutorial today is how choosing the right circuit topology matters, because many times we design these printed sensors. We choose the conventional design that we used using for conventional microfabrication technique. And that's probably something not suitable, because when we're talking about printing, our resolutions are different. The things that our capabilities are different. Um, so this is one example. We were interested to print some chipless RFID, and it's normally used for microwave sensing. And we use chipless RFID based sensor, and normally they have high accuracy, short response time, and the application that we wanted to use it for is liquid concentration measurement. So far the commercially available chipless RFIDs are based on SAW sensors, but these are all time domain. In frequency domain, people have used rather cross-section based design, or insertion law based microwave multi resonator circuit. So selection, and I'll show you why the selection of topology is that important. So we wanted to make something that is in frequency domain. And as I just showed you that in the frequency domain approach, there is only two approaches available. One is RCS based, radar cross section based, and people have demonstrated a lot of radar cross section based approaches. And then there is the insertion loss based approach. In the insertion loss based approach, the most common design is you have multi-resonator that are coupled to a microstrip line. This is the conventional design. And normally insertion loss based design gives better performance than RCS based design. So people like to go for insertion loss based design. But difficulty is for the insertion loss based design. If we go for a microstrip line based design, normally the resolution we want is very difficult to be, and the thickness of the material that the deposited material that we want cannot be supported by a single printer. So that's why if you look into the literature, you will not get too many examples. There is actually none insertion loss based, flexible, chipless RFID. And we started with microstrip line, and you saw just when I was talking about the printing process, how it went wrong because the printer we had available, aerosol printer could get that gap, but not the thickness. So there was a really problem. So then we decided to change our circuit topology. Instead of going for resonators coupled to microstrip line, we wanted to go for coplanar waveguide multi-resonators. So we basically have a coplanar waveguide and we have the multi-resonators embedded in it. And we found that with our substrate and the printing resolution, whatever we have, all this resolution that we wanted can be supported by our printer, and at the same time the thickness. So for a chipless RFID we also need to have two antennas on the chipless RFID. So this is actually the resonator part. We measured, we printed it and we simulated it, and now you can see that we have very nice Q, and the simulation and measurements agree way better than before. And then we also printed the antenna and measured the simulation and the antenna, like compared the simulation and the measurement, and it was something that looking at the return loss that can be used in our chipless RFID. So this is actually the setup that we have for our chipless RFID, and we measured, we basically placed a tube on it, microfluidic line, and we passed liquid on it, and we measured the response of the resonator. These are the transmitter and receiver antenna. And you can see that we basically pass different concentration of isopropanyl alcohol, air and water, and you can see the response, how the response of the chipless RFID changes. So we can definitely measure the differences in the concentration. And this is just a relationship between the concentration and the S21 that we measured, or the resonant frequency of the chipless RFID. And finally, I'm going to show another example. So those PZT, PDMS composite that we used, you saw that we can use as a tactile sensor. But our goal was also to use it as a acoustic sensor for gas sensing or some other type of sensing. So we use them to make acoustic sensors. And as you know, for acoustic sensors, there are different modes. Like there could be surface acoustic mode, flexural plate wave mode, thickness shear mode. So there are different modes. And the reason, out of all the available modes or waves, we used actually the flexural plate wave. And the reason is because for flexural plate wave, you get very good sensitivity. It has higher sensitivity for added mass, and we really want high sensitivity in our measurement, especially when we're going to do gas sensing with it. And another thing also, because for flexural plate wave, you need a lower, a very, very thin substrate, which we can actually produce, because the film that we produced with the spin coating process, they're like 100 to 130 microns thick. So they're ideal for flexural plate waves. So another thing is they have large wavelength and low frequency of operation. And for the large wavelength, the type of IDT we need to print doesn't need very high resolution. So the printer we were using for this didn't have a great resolution, but the large wavelength IDT that we need for flexural plate wave can be supported by the printer. And also another good thing is if we are operating at low frequency, we can actually make the electronics a bit lower cost. So that was our goals to go for flexural plate wave mode. So we made actually IDTs depending. So you can see these are the IDTs that we printed, and we also printed some backplane. So you will see the flexural plate wave sensor in literature, and you'll see that most of them don't have backplane. But as we say that, since already the printed sensor has a little bit of lower performance compared to conventional sensor, we can change some circuit topologies. So we did some console simulation, and we could see that with backplane, we can increase the capacitance and boost the signal. So this is actually electric field with backplane, and this is without backplane. So if we add the backplane in the sensor, you can see we can increase the electric field, which actually can increase the sensor response or sensitivity. So we printed this backplane and the IDT, and we increased so these are the dimensions that we printed, and of course, as I explained, why we had a backplane. So we had a resonator that we built, and we measured that, yeah, it can work like a resonator. And we basically know that this type of resonator, because PZT PDMS has a temperature dependency, so we can use it as a temperature sensor. So just to demonstrate the resonator's functionality first, we use them for temperature measurement. So we put it on a hot plate, increase the temperature, and we measure the temperature with a temperature gun, and we measure the sensor response with a VNA. So these curves just show like example of the response curve for different temperature. And as we plot the resonant frequency versus temperature over time, you can see we have a linear response. So we can measure different parameters from all these. Um, so you can see that we got it, and I don't have that figure here, but we built the same sensor with PVDF, and the response or the sensitivity that we get compared to the PZT PDMS one was way lower. So anyway, I just wanted to conclude here. Maybe I'm a bit over time, but just wanted to conclude here saying that, so there is all these conventional materials that can still be used, but we need to probably do a little bit of modification, or we can come up with materials like new materials by composite technique, and that can improve our material availability and to increase the performance of the printed flexible sensor. We talked about some processes, what can go wrong in the processes, and I wanted to show things from my laboratory um, experiments, that what we did wrong or what we did to improve things. And finally, I think circuit topology as a circuit people myself is very important, because a lot of the conventional design that I used or we used for like with silicon microfabrication technology might not be suitable with flexible and printed electronics area, because of the resolution limitation, and because this is a completely different domain. So we might have to think about the circuit design in a very, very different way. So that's the end of the tutorial, and I hope you get to learn something. And that's it. Thank you for listening, and yeah, thank you again.